Hi friends, welcome back to the course on Introduction to Material Science and Engineering offered by EdupediaWorld. Previous lecture we saw about crystalline and amorphous materials. We discussed about the different crystal structures and Bravi lattice. Today's lecture will focus on three Bravi lattice, two belonging to the cubic system and one the hexagonal system. We'll see in details what is effective number of atoms in each unit cell for each case, their coordination number, what is the percentage packing, and some relevant examples. So let's start our discussion by understanding the body-centered cubic system. With our background of crystal systems and Bravi lattice obtained in the previous lecture, today's lecture will focus on understanding the cubic system. Why specifically the cubic system? Because most of the metals have a cubic kind of crystal system, and then we'll also touch upon hexagonal system because a lot of elements also have hexagonal packing. To begin with, we'll see body-centered cubic. To refresh your memory, when talking about a unit cell, what we do is we consider three perpendicular axes, and a unit cell is the smallest building block, which can be repeated in 3 dimensions to get the whole crystal structure. Okay, so this is the unit cell which will be replicated again and again and again in 3 dimensions to get the whole material, right? So here we will be discussing with regards to the unit cells. So let's discuss about body-centered cubic unit cell. This is a body-centered cubic unit cell. So how do we define a cubic system? A cubic system is basically one in which the 3 dimensions, that is this length, and this length, are equal and the faces are mutually perpendicular to each. That is a cubic system. Now body-centered cubic Bravi lattice is one in which the 8 corners of the unit cell has an atom each, and the center of the unit cell has 1 atom. Okay, so as we can see here, 1, 2, 3, 4, 5, 6, 7, and 1 behind this at the 8th corner are the 8 corner atom, and this atom at the center is the body-centered atom, thereby the name body-centered cubic. Okay, now that we have an idea about the specific structure about a body-centered cubic, let us see how many atoms are there in one unit cell of a body-centered cube. As I just mentioned now that there are 8 corners, but each corner atom is shared by multiple unit cells. Therefore, the whole atom does not belong to this unit cell. To get an idea about how much of the atom belongs to this unit cell, we need to calculate how many unit cells share this particular atom. So let's do that. Let's find out how many unit cells share this particular atom. This atom is shared by this unit cell itself. Second unit cell will be over here to the right of this face. One unit cell will be to the left of this face, and one unit cell will be diagonal from here. So it's like 1 block here, 1 block here, 1 block here, and 1 block here, making 4 blocks surrounding this unit cell. And similar to this 4 blocks in this layer, this layer 4 unit blocks, there will be 4 unit blocks just on top of those individual blocks, right? So 1 layer here, 1 layer on the right of the face here, 1 layer on the left of the face here, and 1 diagonal over here. So just a replication of this, just 1 step on top of it. Thereby what we can say is that this atom is shared equally by 8 unit cells. Same logic can be imparted to each of the corner atoms. Thereby each of the corner atom is shared by 8 atoms. Okay, so its contribution, 1 atom's contribution to this unit cell, this particular unit cell, is 1 upon 8. But there are 8 corner atoms. So the effective contribution of all the corner atoms is 1 upon 8 multiplied by 8. In addition to the corner atoms, there is 1 complete central atom which belongs completely to this unit cell. So 1. This gives me 2 atom per unit cell of a BCC. Now next thing is, let's understand what is the coordination number of the BCC atom. Before that, what exactly is the coordination? Coordination number defines the number of nearest neighbor atoms for a given atom. So the number of nearest neighbors which a particular atom has will be the coordination number of that atom. For this body-centered structure, if we consider the central atom, there are 8 atoms surrounding it at equal distance, the 8 corner atoms. Therefore, the coordination number for a body-centered cubic system is 8. Okay, now that we have an idea about how many atoms are there in a unit shell and what is the coordination number for a body-centered cubic, let us find how effectively are the atoms packed in a body-centered cubic. That is, how much space which is available in the unit cell is actually occupied by atoms. This is quite a trivial mathematical formulation. Let's do it. The side, let me consider it A. If this side is A, all the sides will be A. Let's consider the radius of an atom as capital R. Therefore, the volume of unit cell, what is the volume of unit cell? Is A cube, right? Because it's a cube. Volume of atoms, all the atoms, how much? There are 2 atoms and each atom is of radius R. Each atom will have a volume 4 by 3 pi R cube, which gives me 8 upon 3 pi R cube. Now the volume of atoms is in terms of R, but the volume of unit cell is in terms of A. So we need to find a relation between A and R, and using that relation we can turn A cube in terms of R and find how much percentage of volume is occupied. But how can we find the relation between A and R? That takes us to the idea that we need to find the direction in which the atoms are touching each other. Is it along the edges? No, because there is a gap. Along one of the face diagonals? No, because again there will be a gap. What about the body diagonal? What about from here, pardon me, but this should be a straight line from here to here. What about this? Actually, along this direction the atoms touch each other. This atom touches the corner atom over here, and this atom again touches this corner atom over here. So there is a continuity in this direction. Now once we have found out the direction of atoms touching each other, how can we use it to find the relation between A and R? We know that this length is root under 3A, right? Because this is the diagonal, so root under 3A. But we also know that since the atoms are touching each other, we can find out this length also in terms of R. How come? This will be single R, single radius. This is also single radius, and this is along the diameter, so 2 times R. Therefore total length is 4R. This gives us a relation between A and R. I can write A as 4 upon root 3 R, and this I'll replace here. This gives me 4 upon root 3 cube R cube. So volume of unit cell is this, volume of atoms is this, percentage packing of atoms obviously is volume occupied by atoms, which is 8 upon 3 pi R cube, upon the whole volume of unit cell, which is 4 upon root cube R cube. Since it is percentage, we multiply by 100, and this on simplification turns out to be around 68%. So what we see is a body-centered cubic structure has 68% packing, which means 32% of the volume is void, right? So does it sound like a good packing fraction? We cannot comment on it for the time being. We need to compare it with other packing systems, and only then we can say how good a packing is. 68% packing, right? Now we have idea about the body-centered packing system, the coordination number, percentage pack. Few examples of atoms and elements which has body-centered cubic packing. The most prominent one is iron at room temperature. In addition to that, we have tungsten, molybdenum, potassium. These all are examples of body-centered cubic packing, right? Now with the background of body-centered cubic, let's next see the face-centered cubic system. Face-centered cubic system also belongs to the cubic crystal system. So the sides will be of equal length, and the faces will be mutually perpendicular to each other, as in this case of body centered cubic. The difference will be in body centered cubic you had an atom at the center, body center, and 8 atoms at the corner. In the FCC or the face centered cubic we have 8 atoms at the 8 corners, same as the body centered, but we have 6 atoms at the 6 faces. To make a cube we require 6 faces, right? And each face center will have 1 atom. So the 6 faces, 1 here, over here, 3, 1 at this face, over something over here, 1 at the back face over here, and 1 at the bottom face somewhere over here. So those 6 face centers, 6 atoms, 8 corners, obviously 8 atoms. We have seen the number of effective atoms in a body centered system was 2. Let's calculate the same for the face centered system. The corner calculation will be same, 1 upon 8 multiplied by 8, because it is practically the same thing. But what is the contribution of the face centered atoms? Let us consider this particular atom. This is shared by the unit cell at hand and the unit cell just above it. So every face centered atom is shared by 2 units, and we have 6 face centers. So contribution of each atom to this particular unit cell is 1 by 2, and we have effectively 6 faces, so times 6. This gives us 4 atoms per unit cell. Okay, this is my number of atoms per unit cell. Next up, what will be the coordination number for the FCC? For the BCC you could easily visualize it was 8. For FCC, take my word for the time being, it will be 12, but I will explain it with a much easier to comprehend diagram in a couple of minutes. Before that, let's understand the packing fraction of the FCC. Is it better than BCC, worse than BCC? If better, how much better? Let's do the calculation. This side again, let's call it A. The radius, let's call it R. So the volume of unit cell again be A cube. Volume of atoms in the unit cell, we have 4 atoms, so 4 times volume of each atom is 4 upon 3 pi r cube. That gives us pi upon r cube as the volume of all the atoms in the unit cell. Again, we need to find the relation between A and R to calculate the packing fraction. Now, which is the close pack direction? Is it this direction? No, there is a gap. Is it this direction? As it turns out, actually the face diagonal is the close pack direction, right? So let me draw it here. So this is the close pack direction, the atoms touching each other here and here. Therefore this direction length will give me the relation between A and R. Let me make that calculation. This length is root under 2A, and again there are length R, length 2R, and length R, which is 4R. So root under 2A is 4 times R, which gives A is equal to 2 root under 2R. I'll plug this over here. This gives 2 root under 2 cube R cube. Thereby the percentage packing is volume of the 4 atoms upon the volume of unit cell, which is 16 pi upon 3 R cube divided by 2 root 2 cube R cube multiplied by 100. And this approximates to 74%. If you calculate it, approximately 74% packing in the case of face centered cubic. So we see that the packing fraction is marginally better than body centered. In fact, it is 6% better, but still there is 26% void present in face centered cubic. So what we can say is body centered cubic is not very dense packed. Face centered cubic is better packed than body centered cubic, but still there are a lot of voids left. Now, as we'll see in future lectures, this void spaces which is present due to ineffective packing will come in quite handy while alloying. These are the places where atoms will go and reside in case of alloying with small atom. We put that thought into hold for the later lecture. Now, some of the important elements which has face centered cubic packing are copper, aluminium, nickel, silver. These are face-centered cubic atoms. Now this representation over here, I said that the coordination number is 12 for FCC, but it's quite difficult to comprehend from here. In order to give you a much clearer visual perspective about this, let me handle the question in a different way and let's show you a different diagram. Okay, so this is what is known as a ABC type of structure. ABC. Whenever you hear the term ABC packing, this is also an alternative reference to the FCC type of packing. They both are synonymous. It is just a different way of representation. Now let me give you an idea about what is ABC packing or ABC stacking. So here we have shown 3 layers. The pink layer is the bottom layer. This is layer A. The yellow layer is the middle layer, which is the layer B, and the blue layer is the top layer, which is layer C. Now if I say I give you marbles of equal radius and I say you keep one marble and try to surround it with maximum number of marbles in the same plane, how many marbles do you think you can surround it with? In fact, what you'll find out is that a single marble can be surrounded by a maximum of 6 equally sized marbles in the same plane. That is shown over here. If you consider this particular marble, then 1, 2, 3, 4, 5, 6. This 6 marbles will complete the packing surrounding this central marble, and that is packed to maximum density. Okay, and when you see in such packing, you will see observe there are voids left, right? There is void here, and the void comes in 2 categories. One, let's say, will be something like this, a triangle pointed upward, and another you will see is like this, a triangle pointed down. Okay, now let's say that the first layer is also similar to the third layer, right? So you can use this to visualize the first layer. Though we have some layers sitting on top of the first layer, you can use this to visualize first. So once I lay down the foundation or the layer A over here, I will have 2 options, either this type of hollow or this type of hollow to fill the second layer. Let's, for the sake of argument, say that I picked up this type of hollow to fill the second layer. I filled out the second layer. Now I will again have this type of hollow left over, or the hollow sitting right on top of the base layer or the A layer. So if I go again on top of the A layer for the third layer, then what we get is known as AB packing. That is first layer upper triangle hollow, then again first layer upper triangle hollow, first layer upper triangle hollow. But if we go like this, you lay down the first layer, for the second layer you go for this hollow, third layer you go for the other sided void, then what you get is ABC kind of packing. You have 3 distinct layers. Okay, so this is my FCC kind of packing. As we will see in later discussion, if we go by AB kind of packing, then what we get is hexagonal packing. But let's stick to ABC packing. Now suppose I visualize this from the side. From here, if I see this, then what I will see is a layer, bottom layer like this, a middle layer like this, and a top layer like this. This is what you will visualize. And if you consider this particular atom, this atom will have 6 atoms surrounding it in its own layer, 3 atoms surrounding it on top of it, and 3 atoms surrounding it from bottom. Therefore this particular atom has 12 atoms surrounding it, which means its coordination number is 12, isn't it? That is the basic definition of coordination number. Now there is nothing special about this atom, right? This is a randomly picked atom from the whole set of atoms. Therefore, if the coordination number of this atom is 12, then the coordination number of any atom in a FCC kind of system will be 12. Therefore, what I can say is the coordination number for a FCC system is 12. Okay, I hope this is clear. Now, how can I visualize this turning into this? Quite tricky, right? Let's help you out. Let's imagine just one atom from here, one atom, any one atom, and just the top 3 atoms and additional 3 atoms sitting like this. So 6 atoms in total. Then 6 atoms in total sitting in the opposite direction, the opposite triangle. and one atom just the mirror image 2 layers further upwards, right? And then if you try to join and form the cube, you can see that this is actually a segment of the face-centered cubic. So if you take out some time and try to visualize this, you can actually see how this turns into this, or vice versa, how this turns back to this. But the take home from the discussion here is FCC is one of the most important kind of crystal structure, which has a 74% packing, has 12 as its coordination number, alternatively known as the ABC kind of stacking, because it has 3 distinct layers repeating each time, and packing fraction is better than in the case of BCC, right? This closes the crystal system for the cubic system. Let's jump into the hexagonal system and try to understand that. As I have already mentioned here, the hexagonal system is quite similar to the face-centered cubic in the sense that the basic foundation of atoms, the arrangement of atoms is the same, just the repetition is different. So let me show you here. Here you can see this is my A layer and this is the B layer. Okay, and the third layer is again the A layer. So another atom here, so this atom beneath that in the first layer was also an atom over there, and the fourth layer will be an atom over here, an atom over here, right? Fifth layer again there will be atom over here. So it's AB kind of stacking. Okay, now let us see it's in a different perspective. Like if we visualize it from this, if we see it from this direction, what we'll see is that the bottom layer, one atom at the center and 6 surrounding it, then 3 atoms like this on top of that, and again the bottom layer repeating it, right? So what you can see is this alternatively can be shown over here is something like this, with the central atom, 6 atoms at the 6 corners, 3 central atoms here, and again the 6 atoms with 1 central atom over there. So this gives you the hexagonal packing. Now for the hexagonal packing, what is the coordination number again? You can again think of it in the same way as the FCC. So if you take this atom, 6 atoms here, 3 atoms at the bottom, 3 atoms will be at the top. So for the hexagonal packing system also there will be the coordination number of 12. What will the packing fraction? A similar argument to that of the FCC can be given and said that HCP will also be 74%. Why? Because the packing system or the basic packing pattern is the same, only the stacking sequence is different. In FCC it was ABC, here it is AB, but each layer in itself is packed as compactly as possible, and the second layer is placed on top of first layer as compactly as possible, same as in the case of FCC. So even here the packing fraction is 74%. Okay, now interesting idea is that if this is A, okay, then this height can be calculated as 1.633 A. Fine. Some of the examples of hexagonal packing is, one of the most prominent is magnesium. Then we have others like cadmium, zinc, and zirconium. Such elements belong to the hexagonal packing. Now in fact the hexagonal packing system shown here is not the unit cell. This is not the unit cell. This is basically made from 3 unit cells, okay, with each unit cell following the criteria A is equal to B is not equal to C, and angle A equal to angle B equal to 90 degree, but angle C is equal to 120 degree. So how does it look? It will look something like this. This is made out of 3 unit cell, as I said. So each unit cell will be like this, over here, over here, over here, over here, this way, this way, this way, this way, this way. So this is the unit, okay, and this is the 120 degree. This and this angle and this angle are 90 degree. This is the basic difference between hexagonal, cubic and face centered. The packing pattern is different, the crystal structure is different, and this is defined, this is defined by 3 unit cells rather than 1 unit. Why 3? Why not 1? Because this whole thing shown, the complete system of 3 unit cells shown, much easier to visualize than just one chunk of 1 unit. So this gives you a brief idea about the 3 type of Bravi lattice, that is body centered, face centered and cubic system. I'll not go into further details of each of them anymore now. I'll close the lecture for the time being. I hope to see you in the next lecture. Till the next lecture, have a great day. Goodbye.